Glad you're with us on First Principles Daily, episode 21. Friday, let's wrap the week reasoning from the ground up. Before 1909, nitrogen for crops came from finite mines and seabird droppings. The Haber-Bosch process turned the air itself into an unlimited supply. Before the 20th century, every additional hectare of productive farmland depended on shipments of Chilean saltpeter or Peruvian guano. Those deposits were visibly shrinking with each passing season. The atmosphere overhead held an inexhaustible reservoir of nitrogen. Yet the triple bond that holds two nitrogen atoms together resisted every ordinary chemical attack. Fritz Haber's 1909 demonstration showed that the bond could be broken under high pressure and temperature. Carl Bosch then scaled the same reaction into continuous steel reactors. Together, they removed the last absolute ceiling on global food production. The shift replaced a supply chain whose costs were set by geography and extraction rents. In its place came a system whose dominant expenses became the energy to maintain the reaction conditions themselves. Farmers and agronomists had long treated nitrogen supply as a mining and logistics problem. Guano Islands off South America and the nitrate fields of Chile's Atacama Desert were simply larger versions of the manure piles and compost heaps that had served agriculture for centuries. The convention assumed that usable nitrogen had to be found already fixed in solid form. It then had to be transported across oceans and spread on fields. That assumption locked the entire system into a hard physical limit. The limit was set by how fast ships could move rock and how large the remaining deposits proved to be. Prices fluctuated with every new discovery and every labor strike at the ports. Yet the underlying premise that nitrogen must be dug up remained unquestioned. By the early 1900s, agronomists were openly calculating how many additional billions of people the planet could feed before the Chilean beds ran out. The industry therefore invested in bigger steamships, deeper quarries, and better port facilities. No one invested in an attempt to manufacture nitrogen compounds from the air. The finished price of Chilean nitrate delivered to European farms reflected those extraction and shipping costs, plus the rents earned by the handful of companies that controlled the deposits. No one inside the trade asked what the atoms themselves would cost if the triple bond could be forced open by heat, pressure, and a catalyst. The system treated the scarcity of fixed nitrogen as an immutable fact of nature rather than a solvable engineering problem. Transport alone added substantial cost because the material had to move thousands of kilometers in bulk before it reached the soil. Seasonal shortages and price spikes were accepted as normal business risks rather than signals that the underlying chemistry needed rethinking. Haber began with the equilibrium constant for the reaction of nitrogen and hydrogen to form ammonia. He asked what temperature and pressure would be required to make the yield commercially interesting. The calculation showed that useful conversion demanded pressures above 100 atmospheres and temperatures above 400 degrees Celsius. Those conditions destroy ordinary steel and most known catalysts. Bosch's team at BASF therefore launched a systematic search through thousands of metal oxides and promoted iron formulations. They continued until they found a catalyst that survived those extremes for months rather than hours. The magic wand floor for ammonia is essentially the cost of the hydrogen atoms, plus the thermodynamic minimum energy needed to break the nitrogen triple bond. On that basis, the raw material contribution is only a few % of the price that ammonia commanded in 1913. The idiot index of the pre-Haber supply chain was therefore set by the cost of digging, shipping, and distributing Chilean nitrate. It was not set by any intrinsic scarcity of nitrogen atoms. Once the high-pressure route existed, every subsequent engineering decision could be judged by whether it reduced the energy or the capital required to maintain those conditions. Bosch's first commercial reactor at Opau in 1913 replaced batch autoclaves with a continuous flow of synthesis gas. The gas passed through a series of heat exchangers that recovered the heat of reaction to preheat incoming feed. Later units added better compressor designs that cut the electricity needed to reach 200 atmospheres. Each incremental improvement in catalyst lifetime or heat recovery directly lowered the energy term that dominates the true floor. The process also required a steady supply of hydrogen. BASF initially obtained that hydrogen from coke oven gas and later from steam reforming of natural gas. That step remains the largest single energy consumer, yet it is still far cheaper than importing fixed nitrogen across oceans, because the feedstock is now drawn from air and methane rather than from a single geographic deposit. The supply curve became essentially flat once the reactors existed. A key trade-off was the need for extremely pure feed gases to prevent catalyst poisoning. This required additional purification steps that added capital but still proved cheaper than ocean freight. Another move was the progressive increase in reactor size and operating pressure. That change improved throughput per vessel and spread the fixed costs of the high-pressure shell over more tons of ammonia. Each of these changes attacked the energy and capital components that set the actual floor once the triple bond could be broken at all. The original Haber demonstration used osmium and uranium catalysts that were impractical at scale. Bosch's team replaced them with iron-based formulations whose lower cost and longer life moved the economics dramatically closer to the thermodynamic minimum. The obvious objection that high-pressure equipment itself would be prohibitively expensive was met by designing vessels whose wall thickness and material selection were dictated by the physics of the reaction rather than by conventional fabrication limits. By the 1960s, the process had spread worldwide and the delivered price of ammonia had fallen by more than an order of magnitude relative to Chilean nitrate in real terms. Today, roughly half the nitrogen atoms incorporated into human tissue have passed through a Haber-Bosch reactor. The idiot index has dropped dramatically because the dominant cost is now the natural gas feedstock and the compression energy rather than scarce mineral rents. Even so, the thermodynamic minimum energy to split the triple bond still lies well below current practice. Modern plants achieve roughly 60 to 70% of the theoretical efficiency once heat recovery and catalyst performance are taken into account. The remaining gap is set by the capital cost of the high-pressure vessels, the need for pure hydrogen, and the economic requirement that plants run continuously at very large scale. Those constraints are real engineering limits, not mere legacy habits. The process still depends on natural gas both as feedstock and as fuel, so its environmental footprint tracks the carbon intensity of that supply. Scaling further requires either cheaper renewable hydrogen or continued gains in compression efficiency, neither of which is trivial. The decisive move was to treat the nitrogen molecule's bond energy as the binding constraint rather than the geography of existing deposits. Once that constraint was attacked directly, every downstream cost simply disappeared from the equation. Shipping, mining royalties, and seasonal shortages all vanished once the atoms could be rearranged at will. The same logic applies wherever an industry's price is dominated by the cost of assembling or transporting preformed components instead of by the physics of the atoms themselves. A second principle is that the first workable demonstration must be followed by sustained engineering attention to the energy and capital terms that actually set the floor. Without that follow-through, the initial breakthrough would have remained an expensive curiosity rather than a global industry. Haber's equilibrium calculation identified the thermodynamic target. Bosch's catalyst search and reactor refinements then drove the process toward that target, one incremental gain at a time. Each step lowered the idiot index by replacing rents tied to scarce deposits with costs tied to energy and capital that could be engineered downward. The result is visible in the order of magnitude price drop, and in the fact that half the nitrogen in human tissue now flows through the process. Yet the remaining gap to the theoretical floor shows that the work is never finished once the first constraint is removed. New limits appear and must be attacked in turn. Who will next measure an entire supply chain against the energy required to rearrange its constituent molecules? That's First Principles Daily for today. If this changed how you see what things cost, share it with someone who'd appreciate it, and subscribe wherever you listen. I'm Patrick in Vancouver. One example or one opportunity every day. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.